Hello, class. As someone mentioned, I'll be covering some transient problems because I don't think I covered that during my discussion. So essentially, all a transient problem means is that kind of like an open system, the problem is not steady state. There is like either mass being stored into a system or mass being removed from a system. And here, this problem is exactly that. So let me read it out and solve it from scratch for you guys. So a tank has a volume of 0.85 cubic meters. And I assume this tank's rigid, so this volume will probably carry over throughout all the other states. Two-phase liquid vapor mixture. Okay. I assume I'm gonna say this is the initial state. So I think it's just a hunch. So we have initial temperature. We're given a quality, so I know we're inside that steam curve, basically. Saturated water vapor. So this saturated water vapor. Oh yeah, because like in the mixture, they're both saturated. So saturated liquid and saturated vapor. Okay. Saturated water vapor, it then leaked out through a pressure regulating valve at the top of the tank as energy is transferred by heat to maintain constant pressure. Okay. So it sounds like it's an isobaric process. And I mean, I mentioned this earlier, but let me, sorry, I'll write that later. So then, this continues so the tank is filled with saturated vapor, so full of saturated vapor at the same temperature. Okay, and then yeah, from heat transfer and neglect everything else. I was gonna say, it's isobaric because it's constant pressure, and it's also isothermic based on what we see here. Therefore, my conclusion is that based on like, I guess I'll just do this table or this chart because we're used to it, but we're just moving along the steam curve. We're not moving anywhere outside of it. So that's why we're able to have constant pressure and constant temperature. We're just moving between different quality factors with the same constant lines. And so my guess, or my understanding is that we're moving from a quality of 0.7 to a quality of 1. Okay. I guess this is a bit early for it, but I'm gonna write down the first law of thermodynamics, the updated version for an open system. Change in energy, total energy per time is equal to change is the heat transfer rate minus, I guess it's like the power being done, plus any mass flowing in times, so much variables. GH, yeah, no, it's Z. Minus anything going out. As mentioned, no kinetic, no potential energies, You know what I should do? I should probably draw a picture because I think I can understand what they're trying to tell me here. Okay, the picture is you have this tank, and as I usually draw it, 70 was the quality 0.7, so 30% is liquid form, 70% is in the vapor form, and it's all H2O. And then a tube up here is allowing for only the top part of the tank, which is like the vapor side, to leak out. So only the vapor is leaking until your tank is completely just vapor. All this while there's heat transfer going into the system. Okay. So like, I mean, initially when I look at the problem, I was thinking that, oh shoot, that means like as this gas is leaving, there's some gas remaining, and the heat transfer has to be distributed between the water and the gas itself. That's kind of complicated because I don't really know how to approach it. But then when I thought about it again, I was like, oh, we need to consider the system as a whole, as just 1 and 2, rather than in 1 there's 2 components and in 2 there's 2 components. Before anything, I probably should get my important values. So important values I think would be really helpful to me is I have temperature. From temperature, I will hopefully get pressure, specific volume, total energy, enthalpy. Those are the other variables I really want to get. Pressure is probably the easiest because we know it's in the steam curve. So let me just check the steam curve to see where the P set. There's a P set, yeah, but I think the P saturated is. So 260, right? It's 260. It's right there. 40. I can't have a point, but 46.88. I guess I can do this. 48 point. Because we're given a quality factor that's not 0, 1, I'm gonna write down both the specific volume for the saturated fluid and gas. One, 2, 7, 5. 0.0421. Oh, this sucks. Okay, well, same with internal energy and enthalpy. One, 2, 8, 4. 298. No, 2599. 1134.4. I'm supposed to match the address. 2796.6. 2796.6. Okay. So these are all the values I'm going to be using in a bit. Now let's talk about state 2 because this is way easier. I'm told that everything at the end is going to be saturated water vapor, right? So that means I just need to get the G terms because the G terms are the exact same as what the state is. Don't need to worry about the saturated fluid side at all. So once again, because we're in the same line, I guess something like that. I can use the exact same table to get my values. Oh, I have it. Perfect. Okay, so copy it over. No, that's not what I want. Okay, I don't know how that would work. I usually mention this, but when it comes to work, like some kind of like compressor or turbine is attached to the problem. And that's what causes, it's like the source of power. So I don't know why I highlighted this. I must have been thinking of something else. There's no work being done. Yeah, not sure what that's about. Problem's not, it's not well insulated. Sorry, the system isn't well insulated. So keys here. Total energy will change. If you look at this problem, we have an outlet, but there's 0 inlet, so we're gonna ignore that term as well. Which leaves us with change in internal energy is equal to, right? According to the solution key, your H out is the same thing as your H1 because that's what it is at the start of the system. So my quote unquote guess is that the heat only applies to the vapor side because the vapor side is more condensed and it's at the bottom. So that's what's being affected, not the gas. The gas can stay relatively the same. So okay, with this assumption, we can now continue. Okay, so everything's in terms of what's the word, like a derivative of time. So we're gonna revert that. We just integrate everything with respect to time. So the idea is that you get your original first law of thermal, but with a time derivative attached, or a time term attached to everything. But since, we don't care, we're going to eliminate everything. Okay? I'm going to rearrange my equation. Expand that change in energy term. I move the dot. right. So, technically, I have to explain these two terms out. And let me explain that. Yeah. In fact, the mass of the problem is changing too. So it's technically it's like this. So let's explain these two terms out, and I'll show you what I mean. So in the first case, the total energy, I guess for this second state, what it ends as is, it's mass 2 times internal energy 2, and minus what it initially was, which is mass 1 times internal energy 1. For the other term, the mass out term, it's the difference between those two values. Oh, actually, M1 is higher. So you want to keep that over there. M1's higher. So, because there's a leak, M1 minus M2 times H1. Okay. Notice how right now we have none of these values. But using the things we obtained from the steam table, we can get those values. Let's start with the stuff I think is easier. And that's our U and H terms. Like I said, in terms of the state 2 part, it's easiest. Don't really need that. Actually, so just this. The U2 is equal to UG. U1 and H1 a little bit hard to obtain, but we can still do it. U1 is this plus their quality times the difference between the saturated gas, vapor, and liquid form. I get 2,157.8 kilojoules per kilogram. And how about that enthalpy term? What do I get? $2,297.9 kilojoules per kilogram. Okay. That means all I need left are my mass terms. And to get mass, we're given something way earlier, and it's the volume of this rigid tank. A way to get mass out of it is, remember, we have the term that we always use for thermo is specific volume. And all that it is volume divided by mass. Based on what we have, I didn't get that other term. But based on what we have, we could obtain our specific volume term. And then, with the volume, get our mass. Okay, so I guess I should have solved for that way earlier. But anyway, for state 2, our specific volume is the same as the saturated gas vapor side. Let me get our V1 real quick. And this mess up here should give you okay, 0.2993 there. Oops, that's a right typo. Yeah, so yeah. That's a right O, I guess. Okay, there we go. Hey, as mentioned previously, that's how we obtain our mass terms. So mass 1 is volume divided by specific volume. If I remember correctly, it should have been like 0.5 divided by what we saw for earlier, giving us 28.4 kilograms. So from this amount, we then drop to our second state, which has a specific volume of 0.04221. I'm blanking. Oh yeah, it's got divided. Okay. Resulting in 20.1 kilograms, which is a loss of about 8 kilograms in total. And back to our initial equation. Didn't look good. Let's solve for the final answer, heat transfer. After I bring these things down, because I can't, oh, well yeah, I can just copy. Okay. Minus. Okay, I hope I wrote everything correctly. I double checked the solution, and I actually made a mistake here. The mistake was actually our H1 term. The problem specifies that the leak only happens to the saturated water vapor. When I solve for the exit enthalpy, the out term, or I guess this H1 term, this is the enthalpy for the entire system. The entire system isn't being leaked because, as I mentioned earlier, the liquid, saturated vapor or liquid, stays there. Therefore, our H out is really just our Hg. So I didn't catch that. I mean, I don't know. This will be like a minus 2 or 3 points on the midterm, I'd assume. So, but you know, I'll take the L, and let me write this down to get the right answer. All right, and that's the correct answer. This amount of 14,000 kilojoules were implanted into the system. And that's how this is the first transient problem that I will cover for this recording. All right, now it's on our second and final transient problem for this recording. In this problem, it says an open cooking pot with 0.5 liters of water is at 20 degrees Celsius and 1 bar. So kind of like STP. And it sits on a stove burner. Once the burner is turned on, the water is gradually heated at this heat transfer rate, and pressure remains constant. After a period of time, the water starts boiling and continues to do so until all the water has evaporated. So we're asked to determine the time it takes for onset of evaporation, as well as the time it takes for all the water to evaporate. So yeah, I guess the best way to put this scenario, in at least for picture form, is I mean, I've cooked pasta before, and I think it's a similar concept, but you have a pot of water, so this is your initial state, And then my guess is from what I'm reading, onset evaporation is like your boiling point. So this is probably, what's the word, liquid condensed liquid state, and then it reaches to boiling point, which is the onset evaporation. So then this would be saturated liquid. Oh. And finally, time takes for everything to evaporate. So this would be saturated vapor. And I mean, the gas probably, it would leave the cooking pot because it's like an open system. But, word, yeah. So yeah. So these are 3 states: condensed liquid, and saturated vapor. And from what I'm reading here, it's telling me that each of these 3 processes share a common theme. And that theme is isobaric. Because it tells me that, what did it say? Pressure is constant when the water's turned on and hot water's being heated. So now I take all this information. I guess I put some more stuff down, but it isn't really much. We're just given the starting temperature, starting pressure, and outside of like the state itself, like I guess the word like we want to use is global variables. 0.5 liters, and what's the other one? Heat transfer rate of 0.85 watts or kilowatts. I think we can convert to liters. What's the conversion for liters? 1 liter. So I think it's like 1,000 cubic meters per liter. No, whoops, I got the way around. Okay. Google says it's actually 1,000 liters per 1 cubic meter. Okay, which then gives us a very small number, which I don't want to simplify right now, so we're gonna leave it like this. Okay. Anyways, back to what I was saying. We know everything's isobaric, so if I were to draw my steam curve based on temperature and specific volume, I'm gonna let this be the 1 bar, kind of like the constant line. State 1 starts as condensed liquid, so somewhere down here. It then turns to saturated liquid, and then it goes all the way to being saturated vapor. And then here, that's when you can cook your pasta, is what my parents told me. All right, so we got our states based on this problem, and we can see a picture of it. We're asked to find time it takes for everything to evaporate. Okay, now, oh no, yeah, so something to do with this term, that's why I know. I guess we can write down our first law of thermodynamics. That's what I would do off the rip. Oh, and for at least this one, I'm gonna look between this is just state 1 to 2. So I'm just gonna look at this process, the first process, and for now. Let's copy that. Okay. Yeah, nothing's going in. At least for the process 1 and 2. Nothing really leaves either. So I think we take out this mass flow out term. This is only applicable between the second and third process. Okay, that looks bad. Second and third process. So I guess it just comes down to the first law of thermal that we're used to, the one for a closed system. So I'm not gonna expand it yet. I think I'm just gonna take the integral for now. So I can give everything back to like the normal terms we're used to. Okay, so I would come back to, no, okay, let's come back, okay, it's normal. The heat transfer rate is still, in terms of like a power rate, that one will be associated with the time, and then my work will just be normal work. Okay. Okay, so I mean, this feels like a normal problem to me. I'm gonna find work first and energy. But before that, I probably should get my values. So I'm giving temperature and pressure, which is great. It stays fixed, right? I should specify. So temperature at 1 was 20, and P at 1 was 1 bar. So technically, as we mentioned, it's condensed liquid. So my first step would have been go to table A5, because that's where the condensed liquid properties are. But as far as I'm concerned, the lowest pressure they have there is like 25 or 2.5, 2.5 or 5. But anyways, that's higher than 1. So we don't really have a way to get our values, so we can't use this method. So we're going to make that assumption where, as you see here, this is very close, due to like how this constant pressure line is like sloped, it's very close to this point here. So this is almost the same as 1, like all the properties, specific volume, internal energy, enthalpy, etc. So and by the way, this is based off the temperature. Temperature is what it's based off of, not pressure. So we just take this value and assume that our condensed liquid is like saturated liquid, because water is relatively incompressible in comparison to something like air. So this assumption is, I guess, valid. All right. So going to table A2. And it's sloppy, but I'll make do of it. To go to table A2, at T was 20 degrees Celsius. And what do we get? Okay, well, what was it? It's 20 degrees Celsius, STP. How did I highlight earlier? I did, okay. That's not good. Anyways, it's between these two values. I'll be taking saturated liquid vapor, because that's my assumption. So I'm taking that saturated liquid specific volume and saturated liquid internal energy. Those are the two values I want. Let me write that down. Mm, 1.0018. You fit. Okay. And then I'll take UF. 83.95. Okay, I think I'm writing that correctly. So we can do these values. So this is state 1. This is for state 1. State 2, we're told that, or now we're specifically told onset evaporation, meaning that it is a saturated liquid. However, things have changed, because as this picture, we move up based on how it works. So we can't, that temperature we're given, we can't really use it. But we have, we know it's constant pressure at 1 bar. So we can, this term stays. And, oh man, that's something really cool. What was I going to say? That's right. Now use table A3, which is based on pressure. And we're taking all the saturated liquid values. 1 bar. Okay, so what values I have? Why is it not highlighting? 1.032, what? 432. Okay. 432. Then I'll take the internal energy as well. What was that? 417.386. Okay, I think I have everything I need to solve this problem. I hope. So, coming back to the first law at the very top, you see, I'm going to rearrange it so I can solve for time. What is the time? Oh, that's fine. Change in total energy plus work being done divided by heat transfer rate we're given. We can break this down to just mass. We're given volume, right? Okay, yeah. Mass times change in internal energy. We know it's constant pressure, and then this whole integral equation, but we just basically take out the P because P is constant. Pressure times change in what's the word? Specific volume, and then we have our mass term as well. And then we already have that. So technically, I still don't solve for the mass. And our volumes slightly change, our specific volume slightly change. And because mass is constant, our volume is going to probably slightly change. But I think this is initial, right? So this is probably the initial volume. So I'll use the initial specific volume in order to solve for my mass. And we assume no mass leaves the system in this case, as mentioned earlier in our assumptions. So that would be volume divided by specific volume. And this value divided by this value. And they're both very small, so I should expect something also kind of small. Okay, so I get roughly 0.5 kilograms. Okay, and then now I have everything. Let me plug into my solution and get an answer. I'm going to factor out the mass because easier for me to deal for now. Differences in the U values. Differences in U values. So this is, I probably should label everything then. Difference between the U values. Plus pressure. 1 bar is just 10 to the power 5 pascals. Difference in specific volumes. Okay. Okay. Divide by the heat transfer rate. All the way back up here. 0.85 kilowatts. I believe the kilo here and the kilo from the kilojoules will cancel out, so I should be all right. I'm just pulling this calculator and see what I get. Yeah, it looks good to me. So the final answer, you'll get about 198.6 seconds to get your pot of cold water to the point of boiling point, saturated liquid. So this process from 20 degrees Celsius, which is like room, is that room? Yeah, room. I'm gonna say room temperature to boiling point takes about 200 seconds with using this amount of power to your stove. Okay, so for part B, it's a little different. By the way, this is the process between states 2 and 3. The difference being the mass of the vapor is leaving the system as we go along. So our system, because we define our control volume as like inside this pot, right? So therefore, we have to deal with a mass going out of the system now. All right. Let me just recopy down our earlier equation real quick. I just watched like the recording for the first part, and I speak really fast apparently. So I'm gonna try speaking really slow and let's see if that helps or not. Okay, so there is a mass out. I have to consider this term now. I will now do a very similar process, where once I write everything out, I will integrate them. So I can go back to dealing with values I can understand or can calculate. Because I don't know, rate of change for work, rate of change for energies. I can't really solve for that without being given the time. So we go back to the non-time derivative. This, okay. And there's mass out this time, which is m dot okay, and let me just quickly change this because I'm kind of on autopilot. Okay, I'll take that. So what the dt does is any term that's with respect to the time derivative, kind of like negates it. So then, get back my energy term. I pull up the constant heat transfer rate, put a time next to it. Work goes back to normal. Here, mass flow rate out is not just the mass, like the mass itself, the transient property of it out, times the associated enthalpy value. And similar to the earlier problem, as the system's getting heated and whatever, this thing going out, V out, is just V of the saturated gas. That's all it is. That's what's going out of the pot. So I'm going to now break down this equation we have up here into kind of like values that we can get from either steam table or calculations. So I'll break the energy first. So in this case, we can't really use the form what we did up here, where it's just mass times a change in internal energy and stuff times change in specific volume, because now our mass is also changing. So we're gonna represent it as like the big internal energy. So no, not change. The difference between big internal energy at 3 and minus that at 2. We can maintain our heat transfer stuff because we have that, we try to solve for T. And for this work part, it'd be kind of weird. Essentially, because we have constant pressure. We'll go back to our initial definition for work. We basically put the mass back with the specific volume to form normal volume, pull out the P, and we obtain this following form. For work is just that difference. And then mass going out. Okay, so at 3, everything's evaporated. At 2, it just starts evaporating. So I think it'd be 2 minus 3. And then, as you mentioned earlier, enthalpy out is the same as the enthalpy of the saturated vapor side. Okay, let's quickly talk about some of this control volume real quick. We know that there's no more mass in here. But we can technically also say that there isn't really a volume either, because it's an empty pot. It's a bit weird, but I believe you can say this is true. I need to figure out why it's true. But we can then cancel out a good amount of these terms here. And when I do turn this, I'll break this down as well. The big U, all the big U's is just M times little u. So we take out this term as well. Let me come back to here. Can I logic this out? So what a specific volume is volume per mass. Oh, okay, fair. So volume is mass times specific volume. And because I said mass is 0, then our volume is also 0. I guess that's the reason why volume is 0. I would have thought that there's still a volume there, because I'm looking at this picture and there's a volume still. But based on this equation, I guess, because mass is 0, your volume is 0, based on this relationship. So yeah, I guess that's kind of weird. But something that is true for this problem, and this is how you get the right answer. So got all my 0 terms. I think I have everything but this, which I should have grabbed earlier, but I didn't. That's fine. So I'm going to go back up here. At table 383 at 1 bar, what is our enthalpy during the gaseous form? which one? Oh, wow. Oh yeah, by the way, guys, I'm an uncle now. That's crazy. That's my cousin's kid. He's just born. Um, Enthalpy. G, here, 2675.5. 2675.5. Okay. Trying to solve for T, right? Let me rearrange everything. This is oh man. Okay, so this is negative, but then now it's positive. And then positive, but this is now negative. And I can break V2, as I mentioned, down to mass times specific volume. And this was negative already, so just, yeah. It's a bit sloppy of an equation, but I think it's right. All right. And then I divide everything by our heat transfer rate. Now I plug everything in and solve. I can do that. And mass, at least for initially, this is the same, mass 1 will be the same as mass 2. Nothing has left the system yet. Everything's still there at boiling point. Specific volume. They want to be very specific, get it? And then, I guess that's fine. Oh, I should have factored out the mass like last time, so I should have done. U2 is 417.36. Divide by 0.85 kilowatt. Once again, I think the kilos units will cancel each other out, or they should simplify down so that time would make sense. I think I'll get that in terms of seconds if my SI units are correct. Okay, let's do the math. Wait, hold up, I messed this up way earlier. Okay, that is another L on me. Wow. Basically, I'm supposed to work in kilo units, right? This gives me joules, actually. This gives me joules. So I'm supposed to divide this answer by 1,000. That's what I didn't do. I guess I went a little too fast, but yeah, I missed that. So technically, I want kilopascals. So this should be to the power of 3. It's kind of an L. And let me see if I get the right answer now if I fix that. So now this should give me kilojoules. If I divide, I get the right answer. Okay. Yeah, so, don't be like me. Make sure to check if units cancel out. I swear to you guys, I used to be good at this, but I guess not anymore. But my final answer is 1,327.7 seconds to get my water from the, all water from boiling point to all being vapor. So yeah, this is an example of transient problems where there's mass leaving a system. Maybe I could have shown that problem where mass is entering a system, but it's kind of the same thing. I'd assume you just include that term right here. That's it. But I hope this serves as a good practice. And if it does show the midterm, I hope you guys will be able to get this right. Take care of yourselves, and I'll see you guys on Thursday.